The basic principle behind learning curve is the doubling of production. What was that? Okay. It's the doubling of production. So when production doubles, the decrease in time per unit affects the rate of the learning curve. So when we say double, it's literally double. If, for example, we are given the learning curve at 80%, this means that if we produce the second unit, it will only take us 80% of the time of the first unit. And then if we double this again, so just multiply it by 2, it becomes 4. So the fourth unit takes 80% of the time of the second unit. And then when we double this again, it becomes 8. So the eighth unit takes only 80% of the time of the fourth unit, and so on. So that one is the basis, doubling of production. But in our problems, we don't need to look for the learning curve rate. Like in this case, 80%. This is already given in the problems. So for this basis, we can use this formula. So if you are required to compute for the time that you need to produce the nth unit, all you need to do is to apply this formula. You have T times L to the power of n. T being the unit cost or the unit time of the first unit. So how many hours or minutes did it take for you to finish the first unit or first product? And then times L, L being your learning curve rate, as this is given in the problem. And then to the power of n, n being the number of times t is doubled. So for example, if you are to look for the time required to finish the second unit, your n will be 1 because we only doubled the unit once. But if you are to look for the fourth unit is n will be 2 because we doubled the unit twice to arrive at 4. So let's try to solve this. If the first unit of a particular product took 10 labor hours, and if a 70% learning curve 70% learning curve is present, the hours the fourth unit will take require doubling twice. Why is it twice? Because from 1, we double it once, so it becomes 2. Then we double it again, it becomes 4. So how many hours will it take for us to finish the fourth unit? So using the formula I have mentioned a while ago, that's T times L to the power of n. T is the number of hours required to finish the first unit, in this case, 10 hours. So 10 times L, L is your learning curve rate, in this case, 70%. And then to the power of n. N is how many times the unit was doubled. So in this problem, that's 2. It was doubled twice. So how many hours will it take for us to finish the fourth unit? Anyone? Four point nine, correct. So 4.9 hours na lang. So see, the first time we produced the product, it took us 10 hours. But as we repeat the process over and over again, when we are to produce the fourth unit, it will only take us 4.9 hours. Okay, that means we have learned we have learned how to be efficient in producing the subsequent units. Okay, but however, we should be very careful. Caution should be exercised in assuming that a learning curve is continuing and permanent. So, for example, at the very start of the process, if we assess that the learning curve rate is 80%, it will not always be 80%, especially if there are changes in the process, product, or personnel. Example, we have modified the look of the product So we through innovation, so nagpanindot ta sa ato ang product. So of course, mausab naman pud ang process yung murag back to square one. Okay, so that's why the learning curve rate will also be affected. Or if there's any change in personnel, for example, we added new employees. So new employees meaning faster turnover, faster production. So these things will affect our learning curve rate. Now, the concept of learning curve is useful for internal purposes, external, and strategic purposes. For internal, this is very much useful for labor forecasting. Example, we received a huge order. Say, for example, we are to produce 100,000 units. So we have to forecast how many hours will it take for us to finish all 100,000 units. And then from that, we can decide how many employees do we need in order to finish the 100,000 units requiring such specific number of hours. For external also, this is useful for supply chain negotiations. When you are into manufacturing, of course, you consume raw materials. So for example, we receive 100,000 units of order. So in producing those units, you also have to consider the raw materials needed to finish the 100,000 units. So by studying the learning curve, um, when we when we can assess how fast we can produce the 100,000 units, we can also predict when to order raw materials. So we can negotiate early with our suppliers. And then for strategic purposes, we can assess our performance, our own company performance vis-a-vis the industry performance. So if, for example, our company is, if you feel like the employees in our company are slacking off as compared to the industry, and that might be a good source of decisions for future actions. Then let's apply the learning curve. As I have mentioned, we have three approaches. We have the arithmetic approach, logarithmic approach, and learning curve coefficients approach. So the very first formula I have mentioned a while ago is actually under arithmetic approach. So katong formula itong gihisgot kanina, t times L to the power of n, that's actually for arithmetic approach. And the original basis, which is the doubling of production, is under arithmetic approach. So this one is the simplest approach to learning curve problems. Each time that production doubles, labor per unit declines by a constant factor known as the learning rate or your learning curve rate. Again, for arithmetic approach, this is on the basis of doubling of production. So example, if we know that the learning rate is 80% and that the first unit produced took 100 hours, the hours required to produce the second, fourth, eighth, and 16th units are as follows. So we can either do it manually like this in the table, or we can also use our formula a while ago, nga t times L to the power of n. If we do it manually like this, we can see that when we produce the first unit, we were able to consume 100 hours. When we double the unit, it becomes 2. So since our learning rate is 80%, that means in producing the second unit, it will only require us 80% of the time that we have used in producing the first unit. So since the first unit has 100 hours, 80% of that is 80 hours. So when we produce the second unit though, it only required us 80 hours to finish. And then when we double this again, so that's times 2, it becomes 4. So that means that the time required to produce the fourth unit is only 80% of the time required to finish the previous unit, which is 2. So 80% of 80 is 64, and so on. So if we double 4, it becomes 8. If we double 8, it becomes 16, and so on. We can also use our formula a while ago, t times L to the power of n, so that we don't need to go through each step like this. So if we are to compute for the number of hours used to produce the 16th unit, we don't need to go through 2, 4, 8 na. So let's say, yeah, we are required to compute for the number of hours uh, required to finish the 16th unit. Let's use the formula this time. So T times L to the power of N. T is the number of hours required to finish the first unit, in this case 100 hours, sorry. Then times L, L is your learning rate, 80%. To the power of N, N is how many times the unit was doubled. So to arrive at 16, how many times did you double the unit? So 1, 2, 3, 4. So that's 4. We doubled it 4 times. So 100 times 0.8 to the power of 4. Yeah. So round off, it's 41. Okay? 41 hours. Now, arithmetic approach is only useful if we are to compute for the number of hours required to produce n units, and that n is one of the doubled values. It's like 1, 2, 4, 8, 16, and so on. But what if we are to look for the number of hours required for any units that does not belong to the doubled values? Say for example, pangitaan taog number of hours for the fifth unit. So dire wala may labot si fifth unit because it's not one of those doubled values. So that's the limitation of arithmetic approach. It does not always tell us how many hours will be needed to produce other units. For this flexibility, we must turn to the logarithmic approach. So we will be discussing the second approach this time. The second approach is what we call the logarithmic approach, and it is computed using the following formula. T sub n, time required to finish the nth unit, is equal to the time or the hours to produce the first unit, then times n to the power of b. N here represents what unit. So for example, if it is the third unit, n is 3. And then to the power of b being the slope of the learning curve. So slope is logarithm of the learning rate over logarithm of 2. Logarithm of the learning rate over logarithm of 2. That is our b. Okay. Let's have this example. The learning rate for a particular operation is 80%, and the first unit of production took 100 hours. The hours required to produce the third unit may be computed as follows. So since we are to compute the hours required to finish the third unit, so that's Tn, we will replace n with 3. The time required to produce the third unit is equal to T1. So yeah, the time required to finish the first unit is 100 hours. So that's 100 hours times n to the power of b. Again, n here is 3. B is your slope. So that's logarithm of the learning rate. In this case, learning rate is 80% over logarithm of 2. So it will give you 70.2 labor hours. So we need 70.2 hours to finish the third unit. Okay. So that is logarithmic approach. The third approach is learning curve coefficient approach. The learning curve coefficient technique is expressed in the following equation. So if you notice, for the three equations, somehow the same lang ang first part. So Tn is equal to T1. Then what really changed is only the last coefficient, or the last variable rather. So for For the arithmetic approach, the last variable is L to the power of n, right? L to the power of n. For logarithmic approach, the last coefficient of the formula is n to the power of b. In this case, for learning curve coefficient approach, the last variable is c. C representing your learning curve coefficient. So for the learning curve coefficient, we need to look at this table. It's quite overwhelming, but this is really easy lang. So on the topmost portion of the table, you can see the learning rates or the learning curve rates. We have 70%, 75, 80, 85, and 90. And for each particular learning rate, we have two subcolumns, so unit time and total time. So you will look or you will use the unit time column if what is asked is the number of hours required to finish a particular unit. So example, if the learning rate is 75%, okay, let's say 75, and then you are asked to compute the hours required to finish the third unit only. So you will look at 75% and then you match it with the number of units. So in this case, 3, in my example, 3. So 3 under 75% is 0.634. And that is your coefficient. Again, you will use this if what is asked is the number of hours required to finish that particular unit. What if the problem will ask you, how many hours will it take for you to finish all 3 units? So from the first unit, second unit, and then third unit. So all 3 units. How many times will it take for us to finish all 3 units? So you will look at the second subcolumn, which is your total time. So your coefficient this time is 2.384. Okay, so that will be the coefficient that you will use in the formula. Let's have this example. It took a Korean shipyard 125,000 labor hours to produce the first of the several tugboats that you expect to purchase for your shipping company, Great Lakes Incorporated. Boats 2 and 3 have been produced by the Koreans with a learning factor of 85%. At $40 per hour, what should you, as the purchasing agent, expect to pay for the fourth unit? So, we are to pay daw 40 per hour. $40 per hour. So, para makakompute ta pila tong bayro nun, we have to know how many hours, diba, to finish the fourth unit. So, this is learning rate is 85%. What is our formula again? So, our formula is T sub n here is 4 because we are trying to look for the fourth unit. So, T sub 4 is equal to T sub 1. So, how many hours did it take first to finish the first boat? That is 125,000 hours. Then times C. C is our coefficient. In this case, what is asked is only for the fourth unit, not total 4 boats, only the fourth boat. So, let's look at the table again. So, again, our learning rate is 85%. So we have to look at the 85% column. So under 85%, we have to focus on the first subcolumn, kaning unit time, and then look for the fourth unit. So the number 4 here is 0.723 under the 85% learning rate. So 0.723. That is now our coefficient. So this will now be our formula. 125,000 hours times 0.723. If you compute that, you will get 90,375 hours. So that's how many hours required to finish the fourth unit. So, and since we are to pay $40 per hour, so just multiply $40 per hour to the number of hours, 90,375. So we have to pay a total of 3,615,000. Okay. Then the next question is, how long will all four boats require? This time, all four boats. So from the first boat, second boat, third boat, and fourth boat, pila ka hours ang kailangan? So let's look at our table again. Under 85% learning rate, this time focus on the second subcolumn, total time. So total time for under 4 units, you have coefficient 3.345. So 3.345, that is our coefficient. So 125,000 times 3.345 is equal to 418,125 hours. That means these are the number of hours in total to produce or finish all four boats. Okay. Then what happens if our most recent or most reliable information available pertains to some other unit? This is when there are changes in our production or process. So Kita, Great Lakes, believes that unusual circumstances in producing the first boat imply that the time estimate of 125,000 hours is not anymore a valid base as the time required to produce the third boat. Boat number 3 was completed in 100,000 hours. So this means that there is a discrepancy, diba? If we have, if we are to use our formula, katong T1 times coefficient, and then if we are to use that to compute for the number of hours required for the third boat, it will not give us 100 hours. Let's try ha. So that's 125,000 hours, then boat number 3. If tan-awin mo ang coefficient sa 3 under 85%, the coefficient is 0.773. 0.773. So 0.773, let's multiply that to 125,000 hours. It will give you only 96,625, right? So 125,000 hours times 0.773 is only 96,625. But when we finish the third boat, the total hours that we have spent in assembling the third boat is actually 100,000 hours. So we can observe that the basis kaning T sub 1 nga 125,000 hours is not anymore a valid base. So what we are going to do is to recompute another base. So since 100,000 hours man for boat number 3, that's 100,000 divided by 0.773, the coefficient that we have we looked for in the table of coefficients. So 100,000 divided by 0.773 will give us 129,366 hours. So what does this mean? Since this is our revised base, if we were to compute boat number 4 number of hours, we will not use anymore 125,000 hours, the original hours, but rather the revised base of 129,366. Okay. The limitations of learning curve. Learning curves differ from company to company as well as industry to industry. That's why you should not use someone else's learning curve rate. Okay? You have to develop your own learning curve rate. Then learning curves are often based on the time necessary to complete the early units. In fact, when we look at our formula, very crucial you'd see T sub 1, right? Therefore, those times must be accurate. You have to accurately record the number of hours required to finish the first unit. And then any changes in personnel, design, or procedure can be expected to alter or change our learning curve. And then it doesn't always apply to indirect labor. Indirect labor. When we say indirect labor, these are the number of hours consumed by workers who are not directly involved in producing the product. Okay, so for example, the mechanics, the hours consumed by the mechanics or our supervisors, for example, are referred to as indirect labor because these people don't actually um, are don't actually involve themselves directly in producing the product. Murag support lang sila. Then the culture of the workplace as well as resource availability and changes in the process may alter the learning curve. For instance, as a project nears its end, worker interest and effort may drop, curtailing progress down the curve. So like normal life situations ba? Example, at the very start of the semester, medyo hyped up pa, so ganahan pa mag-study, but as the semester is about to end, mawagtangan na motivation. So same lang po na sa workplace. Kung bago pa lang ka naghimuan nga work, let's say fresh grad ka, then first job nimo, of course enthusiastic pa kaayo ka, but then as time passes, mawala na ka na og motivation. So because of your loss of interest and motivation, that will also affect your efficiency in your work. Okay? So now there are human factor po. So that's why we can say that whatever is the assessed learning curve rate at the very start of the production will not always be the same learning curve rate as the production progresses. Okay? So that's the end of our topic for learning curve. Do you have any questions? So next week, we will start with another topic, and that is linear programming. So the topic linear programming is quite long, so it might take us 2 weeks to finish linear programming. If you notice, kaning topic na learning curve, this is not found in the Anderson book, but the topic linear programming is there, na dito sa libro. I think it's 4 chapters sa libro, linear programming. Yeah, so we will meet again on Thursday next week, the same time, for our synchronous session. So, do you have any questions before we end our class?
None so far, miss.
Okay. Sige, thank you and enjoy your morning.
Thank you, Miss.
Thank you,
Thank you,
man.
Thank you,
Miss.
miss. Thank you.
Miss.
Thank you.